Hello, welcome to my video on what I'm going to call single replacement reactions. Single replacement reactions generally involve a single element and a compound. So if you look here, the general form would be and oftentimes I'm going to be dealing with a metal and a compound where you have, it's an ionic compound where you have a metal and some sort of a cation, some sort of an anion. And what will happen is if the metal that is by itself is a stronger oxidizer, or I should say oxidizes more easily than the metal in the compound, then what will happen is it will replace the metal that is in the compound by losing electrons. And I'll teach this to you in a later video, but the loss of electrons is what we call oxidation. So this atom will lose its electrons to the atom that is already in the compound. This will then become neutral and then come out as an atom. So a lot of times when you're doing these reactions, if you have a metal, you'll literally see the metal that was in solution coming right out of solution. The metal that loses its electrons and becomes positive then joins in with our anion to form a new compound. Now, how do you know which metals replace others? You generally are going to have at some place where you can reference a list of oxidized, ease of oxidation of metals. The metals at the top oxidize most easily, the ones at the bottom least easily. So what ends up happening effectively then, anything above that is by itself will replace anything below that is already in a compound. So let's look at some examples of this. Here I have zinc by itself. Here I have copper in combination with a sulfate. Well, the question is, if zinc will oxidize more easily than copper, it will replace the copper will be by itself, and then the zinc will combine with the sulfate. So we have to come over here and take a look. And if you notice, here's zinc, and copper is down here. So zinc is above copper, so zinc can replace copper. So for that reason, the zinc will replace the copper. So what I do over here then for my products, if I'm trying to predict the products, is I'm going to take this copper and put it by itself, because it will now not be in the compound and it will be by itself. And then I look at what's left and I say, well, I'm going to combine the zinc and the sulfate, and then you follow your rules for writing ionic compounds, again, which I've discussed in previous videos. Zincs have a +2 charge, sulfates have a +2 charge, so then my formula would be 1 zinc and 1 sulfate. And so I was able to predict these products based on what I saw over here. Now let's look at another example. Lead and magnesium nitrate. Again, I'm going to compare the metals. So I'm going to take this lead and say, is it more active or a stronger oxidizer, or able to oxidize more easily than the magnesium? And if so, this reaction will go forward. So we come over here and we find our lead. Here's lead right here. And my magnesium is all the way, it's a very active metal, it's up here. And by the way, just to point out, notice that a lot of your active metals, these are your column 1, column 2 metals, your alkali metals and alkaline earth metals. And again, those are atoms that are maybe 1 or 2 electrons away from having a full shell. If they can lose them, they tend to do so, and since they can just lose 1 or 2, they do so rather easily and tend to be very strong oxidizers. They tend to want to get rid of their electrons very, very easily. So anyway, so my question is, can lead replace magnesium? Well, if you notice, lead is below magnesium, and so therefore it cannot replace it. So what I would do for this reaction is you could leave it blank or something. I'm just going to simply write NR, no reaction. This will not occur. No reaction will occur because the lead cannot give its electrons to the magnesium, and so no reaction will occur. Here's another example. Here's silver, acetate, and lithium. And again, if we notice lithium, wow, that's way up here. That is a very, very active metal. That could replace pretty much anything. So I know without even finding silver, I know this is going to occur. But if I were to look for silver, notice silver is down here at the bottom. And again, by the way, notice the metals at the bottom, the silver, platinum, gold. These are your jewelry metals. The reason being they're very inactive metals. They really can't oxidize with a lot of other things, give their electrons to a lot of other elements, and so therefore they don't react very much, which makes them perfect for jewelry. If you made jewelry out of these elements, they would react very, very quickly and would not last very long. These last a long time because of their inactivity, as it were. So I know lithium is going to replace the silver. So basically what I need to do is say, all right, well, lithium will replace it, so my silver will be by itself. So I can just do the Ag. And then the lithium will combine with, this is an acetate. Now I have to write my formula based on the charges that I know. Lithiums are alkali metals, they're +1. Acetates are -1. So I just need one of each. Please note also that the metal will go first, the cation will go first, and the anion will go second. So LiC2H3 O2. And so that is lithium acetate. Now, what I want to show you here is this can also happen with your nonmetals. Notice I have chlorine and bromine. Turns out nonmetals can replace each other as well, and if you'll notice what happens here is fluorine can replace chlorine, chlorine, bromine, bromine, iodine, and iodine can replace sulfur. This is the exact order of the halogens here, and so sometimes you don't even need an activity series. You can kind of see these guys going down. So what ends up happening is chlorine is above bromine, and in this case it's not going to replace the metal, but it will replace the non-metal. So what I'm doing is I'm replacing the second thing in my equation. So what I do then is I write the formula for K and Cl. Potassiums are alkali metals, they're +1. Chlorides are -1, they're halogens. And then what's going to be left by itself is bromine. Going back a few slides, though, I told you that when you write hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine by themselves, you must make them diatomic. So we're going to have to put a 2 there. So in balancing this, of course, then I'm going to need 2 there and 2 there. Now for my next one, I have an acid. This acid is hydrofluoric acid. If you remember a few videos ago, I taught you acid naming, and in this case this is a fluoride ion, and the way we name acids that use an anion that ends in an IDE, we basically put a hydro in front and then an ic acid at the end of the name. So this is hydrofluoric acid and calcium. If you look here, you'll see that calcium is a very, very active metal. It is very high. We do include hydrogen in these activity series because it behaves like a metal in a lot of cases because it's positive. And so what will happen is calcium is very capable of replacing hydrogen. So what I'm going to do then, again, the hydrogen will be by itself. And again, this will be diatomic. Remember I said here, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and hydrogen are all diatomic. And then I'm going to put the calcium with a fluorine. Calcium is +2, it's an alkaline earth metal. Fluorides are halogen and they're -1. If these are +2 and these are -1, I'm going to need 2 fluorides to get this to add to 0. So it's going to be CaF2. To balance this, you can see I have 2 H's and 2 F's on the right. So to get that, I put a 2 here. Now another way for me to do these problems is to not give you the formulas, but to actually give you the names. And then you have to go back and know how to write the names. And again, I've discussed that in previous videos, and for my students, we do that in class before we do the predicting here. But what ends up happening is you just simply say, all right, well, it's magnesium. That's rather easy. It's simply an element, so you write Mg. Nitric acid, again, going back to my acid naming video, ic acid is based on the 8 ion. I ate it and ick, I felt icky, or however you want to remember that. So the nitrate ion, if you look that up somewhere, is an NO3. It has a -1 charge. Acids always have an H at the beginning for my positive thing, so nitric acid is HNO3. So then your question becomes, can magnesium replace the hydrogen? Again, we go over here. Here's our magnesium, here's our hydrogen. The magnesium is above the hydrogen, so it can replace it. So it will do so. The magnesiums are +2. The nitrates are -1. Since I need 2 nitrates, and nitrate is a polyatomic ion, I must put it in parentheses and put a 2 on the outside. So again, these are +2. I need 2 of these at -1. Since it's a polyatomic, I put it in parentheses with a 2 there. And then again, just like the previous problem, the hydrogen will now be by itself, and so I'm going to have an H2. For my last one, I'm going to have sodium chloride. And again, sodium is +1, it's an alkali metal. Chlorides are halogens at -1, so that's salt. A lot of you know that. That's simply NaCl. And aluminum is Al. When I put these together, again, I come over and I reference, is aluminum, I'm sorry, more active than sodium? Well, here's aluminum, but if you'll notice, sodium is above it. So it turns out that, again, aluminum is incapable of replacing or giving its electrons to the sodium, causing it to come out of solution. So what ends up happening is, again, this one would be no reaction. All right, one special case I do want to mention here, and this primarily applies to my honors students, and as I've said before, with the honors classes, I'd like you to know some specific examples. One of the cases is when you have an active metal, say sodium, reacting with water. What ends up happening is the sodium is going to replace the hydrogen. And notice the sodium is up here, it's more active than the hydrogen is down here, so it can replace it. But when the sodium replaces the hydrogen, it does not replace both H's. It only replaces one of them. So my products end up being a metal hydroxide. In this case, my metal is sodium, so it's going to be sodium hydroxide. This is the polyatomic hydroxide, which is -1. Sodiums are +1, so one of each. Plus hydrogen, but as I've said before, when you put H by itself, you need to write that as diatomic. Now I do need to go back and balance this so everything works, and so what ends up happening is I would say I've got, let's see, I need 2 of those, 2 there, I've got 4 H's, I've got 2 O's, and so I need 2 sodiums. So again, that's just a special case of a single replacement reaction that you should be familiar with. Thank you very much. My next video will be on double replacement reactions.